Hello, my name is Nicholas Tehirina, and this is going to be my presentation over gain scheduling in LQR with an LQE to make an LQG compensator system. The LQG system is going to be applied to the 3-degree airfoil that you see in the bottom left, where you have angle of attack alpha, H is going to be the plunge, and beta with the lift and moment acting at the elastic axis. And we're going to be analyzing flutter on the 3-degree freedom airfoil. And what is flutter? Flutter is caused by the mutual coupling of inertial force, elastic force, and aerodynamic pressure when the pressure is exposed to airflow. So like the demonstration that was shown in class where the wings are flying in the sky and they start flapping and vibrating and lead to instability. So adding controller to the system can delay or prevent the appearance of flutter, and we're going to be using gain scheduling on this airfoil to show the effectiveness of that. So as far as the literature review, this is going to be talking about how active research in the industry is for the LQR and LQE for the Gaussian controller. So this has been going on since like the 1960s. There's a paper from 1977 that talks about it, but the paper that we're going to be talking about that with the control of air elasticity is going to be the robust scheduling control of air elasticity and the application of the LQG and H infinity gain scheduling technique for active floater suppression. So those are the ones we're going to be referencing for the 3-degree freedom airfoil and the technique to actually gain schedule and even curate the LQR LQE system. So as mentioned before, the states are going to be the plunge H, the angle of attack alpha and beta. Um, we're going to be using the equations of motion seen earlier to then put them into a state matrix and input matrix, where the state matrix depends on the velocity and angle of attack. So the system is nonlinear due to the fact that alpha, the state matrix is a function of alpha. Um, so we're gonna have to analyze the system at a fixed angle of attack, which is going to be 10 degrees, and we can vary the velocity to see how the velocity at a certain angle of attack can affect the system. So for the open loop, you can see how the eigenvalues evaluated at a velocity but a static angle of attack. The system is unstable with the positive eigenvalues. And whenever you close a loop using the gains from the LQR, you can get the closed loop holes from the LQR using the gain from that's outputted by the LQR that's solving the Riccati equation behind the scene. And then you can use that to then close the loop and get the desired values of making the system stable. So connecting what I was talking about earlier with the eigenvalues and closing the loop with the static gain K from the LQR, you can either have it static or a gain schedule to where based on the velocity, you can have it changed to a gain that's more preferable for those operating conditions. So you can see with the static gain on the left, the open loop is seen to be unstable at around 9 meters per second, with a static gain is around 28.1 meters per second. And whenever you go and gain schedule it once, you can get a delay of a couple meters per second to 37.5, which is higher off of just gain scheduling the system once versus having a static gain. So the results you see here are gain scheduling the system 3 times. You can see how going from 28 meters per second off a static gain to 37.5 for gain scheduling at once. So then 53.4 off of gain scheduling at 3 times. Again, it has to do with making sure those eigenvalues they go unstable for the like how the open loop system goes unstable at 9 meters per second. Continuously scheduling the variables to the gain to change based off of the operating conditions, which is going to be the velocity. You can then again show how effective the gain scheduling technique is in delaying the instability of the airfoil. So this slide is to just go over what an observer is. It's a system that provides an estimate of the internal state of a given real system based on measurements and outputs and control variables of the real system. You have a diagram on the bottom where you have AX plus BU being the operating system, the state matrix and the input matrix, which is then fed into C. which is going to be the output that you're going to be measuring. So in our instance, since we're doing an observer design, we're going to be measuring just a first state plunge, and that is fed into the observer equation that you see at the bottom, A minus LC. But in that equation too, there's also a different C that is then an identity matrix observing all the states, so that way the estimated states that get outputted can then be multiplied by the gains that is outputted from the LQR. Depending on the velocity that the system is operating at, the gains K multiplied by the estimated states for the control law will change, depending on the gains that are being used, so the system can be optimized. For our system, again, since it is going to be an LQE, LQR system to make an LQG, the LQE is a common filter specifically, where it's estimated full state feedback with the system from noisy sensor measurements. So we're also going to be injecting white noise into the system, so that way the common filter can act as a filter for it, and still gives the estimates with the LQR being gain scheduled. And this also too, it's just some more background information on the equations of how it works. So the A minus BK is again closing the loop with the gains from the LQR, minus LC, where the L is going to be from the observer gains from the LQE. And it forms the new state matrix A minus BK LC, and A minus BK minus LC that determines the new stability for the eigenvalues. You can see the control law is going to be again y, or not y, u is equal to negative k x hat. So this is going to be the observer results for the LQE, where on the left you can see how without tuning the system, it just oscillates repeatedly until past the 5 seconds for the simulation that's ran. It takes a while for it to go to steady state, whereas opposed to the right, where the system got tuned based off the different weight matrices that got inputted into the LQE, and also gain scheduling. You can see how there's a couple oscillations, but then it goes to steady state around 3 seconds. So the system is operating significantly better as opposed for the left, and then it has to do with the fast convergence of the system based on the right. So the same trend for the delta alpha can be seen where on the left, without any observer tuning, you can see how many oscillations occur and it doesn't go to steady state, whereas opposed to whenever we tune the system, again, as before, the delta alpha significantly has a little bit of overshoot, but then goes to steady state again at around 3 seconds to 3.5 seconds. The same thing can be seen for beta, where significant oscillations occur and the system doesn't go to steady state, versus the right, where the system got the observer got tuned. There's a little bit of overshoot, but then the system goes to steady state again at around 3 seconds to 4 seconds, showing that the tuning of the system versus not tuning the system shows effectiveness, and also gain scheduling plays a part in how fast the system converges to from the observed states to the true states. So the Simulink model was included, the closed loop, so that way I can try to get a better understanding of how Simulink works, and so that way it could also give more of a visual of how the code is working versus just looking at code and seeing it run. So you have the actual system where you have the state space system at the top that's also fed in with white noise. That is being observed in the output, which is also being fed into the state observer, where again the C for the state space system is just going to be observing the first state, the plunge, and then that's fed into the observer system, where it's using the common filter gains, KL, where it's then outputting the estimated states, which is then being multiplied by the LQR gains that are being scheduled based off of the different operating conditions, which again is going to be the velocity. So based on the velocity, is going to be changing the gains, which then changes the control law, which is then fed back into the actual system and the state observed system, so that closing the loop, and then it's continuously estimating, so that way the estimated states can be can converge to the true states, and all that's being observed on the scopes on the right. So these are the results from the Simulink observer output with the gain scheduling. This is for the state plunge, where you have meters on the left and time seconds on the bottom. You have the true states being outputted as a yellow line and the observed states as a blue line. There's some undershooting for the system before it converges at around 1.5 seconds. My guess is because of the fact that the noise that's being injected, it's obscuring its ability to actually properly observe the system until it gets properly filtered out, and then it could actually go to the estimated states. So this is the results I get for plunge. So the pitch angle gets tracked actually pretty well, where you have degrees on the left and time seconds on the bottom, where the true states are in yellow and the observed states are in blue. So this, even starting at different initial conditions, the system gets tracked pretty well with the common filter acting very well and properly observing the states while the system is going with the LQR. The same thing can be said for the trailing edge, where the output is in degrees on the left and the time is round on the bottom, where again the system gets tracked significantly well. I don't think the noise is affecting this state very much as it is the plunge. But the system attenuates very fast and then goes to steady state. Uh, so for the discussion slash conclusion, we're showing the successful implementation of a common filter observer with an LQR designed in a closed loop system, where the LQR is being gain scheduled in order to create the LQG Compensator system, where again the LQR is being solved in one fashion and the LQE is being solved in a different fashion, utilizing the separation principle. So that way the systems can be designed individually, but then operate together to form the compensator for the filtering out the noise. We show successful Simulink modeling to give more of an intuitive representation of how the common filter with the gain scheduled is implemented, and how the resulting system has optimal sensor-based feedback for the 3 degree of freedom airfoil.